In this video, we're going to go over a couple of examples of asymptotic expansions. These will be covered from the ground up in part 3 perturbation methods, but it'll be really helpful for you if you've seen some examples of these before you go into the part 3 course, as it moves relatively quickly, so it'll be a lot more straightforward if you're not going into this blind. Now, we'll cover a regular perturbation example and a so-called singular perturbation problem as well. We'll come to what those mean as and when we need to, but this one will be a lot less teachy than the other videos, and we will learn by doing. So to start with, we're going to consider this quadratic equation here with a small parameter epsilon. Now, the structure of this equation is the same no matter what the value of epsilon, and we'll see why that's important much later on. But it will always have two roots. They might be repeated roots, they might be complex roots, but it will always have two roots. And in fact, we can use the quadratic formula to find an explicit expression for the roots, which we can then expand in a power series in powers of epsilon. And we want to find another way of finding this power series. Now, for more complicated problems, we might not be able to get the analytic approximation here, or the analytic result here, so we need to find a power series solution to any given equation. And the way we do that is just by postulating a solution of the form x is x0 plus epsilon x1 plus epsilon squared x2, and so on. So when we plug that into the equation here, this becomes x0 plus epsilon x1 plus epsilon squared x2 plus ... all squared plus epsilon x0 plus epsilon x1 plus ... And I've truncated that one early because we're only going to be working up to order epsilon squared here. Minus 1 equals 0. Okay, let's look at the terms of this equation at order 1, at the leading order. We have an x0 squared, and we have a minus 1 equals 0, and so that gives us that x0 is equal to plus or minus 1. Let's look at the terms at order epsilon. From this bracket, or this squared bracket here, we get 2x0 x1. We've got an x0 times epsilon x1 and an epsilon x1 times x0. And from this term here, we just have an x0. And this has to, the terms of order epsilon have to sum to 0. So because we know that x0 is non-zero, we can divide through by x0 and end up with x1 equals minus 1/2, irrespective of the value of x0, well, whether it's plus or minus 1. At order epsilon squared, we have a contribution from the epsilon x1 squared term, so we have, this should be x1 squared. We have a contribution from x0 times epsilon squared x2, so that's 2x0 x2. And we have a contribution from the x1 here, equals 0. And when we plug in this value of x1 and this value of x0, we end up with x2 is equal to plus or minus 1/8. This plus or minus takes the same sign as plus or minus 1, so perhaps it's better to say it's equal to the sign of x0 times 1/8. Anyway, you can see here that the power series we found, or the power series solution we found for the two roots here, is exactly the same as what we get from the analytic solution, which of course is what we'd expect, but it provides a good check on results. And like I said, not all of these problems have exact solutions. The key power of taking an asymptotic expansion is you find a series solution for something that does not have an exact solution, but in this case we can just check our answer against the exact solution. So now let's consider a different problem. Let's consider a so-called singular perturbation. In this case, we have a cubic equation, but when epsilon equals 0, it becomes linear, and so we only have one root. But when epsilon is non-zero, we have up to 3 roots. So there's a bit of a, or rather, I suppose we have 3 roots. They could be repeated, they could be complex, but we have 3 roots. So the qualitative structure of the algebraic equation changes based on the value of the parameter, and that's what makes this perturbation singular. So let's start out up here by attacking it exactly the way that we attacked the last problem. So we'll take x to be x naught plus epsilon x1 plus epsilon squared x2, and plug that in and work at order 1 in the equation to start with. And order 1, we're just left with minus x naught plus 1 equals 0, and so that tells us that x naught is equal to 1. At order epsilon, we've got x naught cubed minus x1 equals 0, and so that implies that x1 is 1. And at order epsilon squared, we have 3x0 squared x1 minus x2 equals 0, so that implies that x2 is equal to 3. This comes from expanding the cubic term here. I won't go into the detail on that, but this gives us a result that's x is equal to 1 plus epsilon plus 3 epsilon squared plus dot dot dot. But this just gives us one root, and this is a cubic, it has 3 roots, so clearly something is going wrong here, we're missing some roots. We expect that when epsilon goes to 0, our one root is at x equals 1, so this is a valid root, but what's happening to the other two? And this is what makes the problem singular, like I said, and the way to find them is to turn this into a regular problem. And the way we do that is we assume that x is equal to delta, and we'll find out what delta is later, times some capital X, where capital X is an order 1 quantity. So if we substitute this into the equation here, we have epsilon delta cubed x cubed minus delta x plus 1 equals 0. And we want to find the dominant balance. So what are the two terms that balance in this equation dominantly? So in the last problem, we had an epsilon on the end, so the dominant balance was between the first two terms. So what about if epsilon delta cubed x cubed balances the 1? What if they're the dominant two terms? Remember that x is order 1, so that means that delta has to be order epsilon to the minus 1/3. But that implies that delta x is equal to order epsilon to the minus 1/3, which is much, much greater than 1. So that's a contradiction, because if we take the dominant balance between the first and the last term, the middle term is actually even bigger, so that's silly. If we take the dominant balance between the last two terms, we have delta x goes like 1. Well, that implies that delta goes like 1, and that's silly as well, because that just returns us back to the problem we had in the first case. So the dominant balance has got to be between the first two terms. So we have epsilon delta cubed x cubed has to balance delta x. And in that case, we had to have delta goes like epsilon to the minus 1/2. Okay, so x is equal to epsilon to the minus 1/2 times this capital X, where, subbing in this value for delta into the equation here, we have epsilon to the minus 1/2 x cubed minus epsilon to the minus 1/2 x plus 1 equals 0. Okay, let's multiply through by epsilon to the 1/2, and we get x cubed minus x plus epsilon to the 1/2 equals 0. This is a regular problem because we've no longer got our small parameter multiplying the highest power. We're just left with something a little bit like what we had before. But caution, we've got non-integer powers. So capital X, we have to postulate a power series of the form x0 plus epsilon to the 1/2 x1 plus epsilon x2. We can't go up in integer powers anymore. We find these capital X0, capital X1 and capital X2 in exactly the same way as we did in the previous regular perturbation problem. Let's just find capital X0 for illustrative purposes. We have x0 cubed minus x0 equals 0. So x0 minus 1, x0 plus 1 equals 0. Now remember that capital X is order 1, so x0 can't be 0 as capital X is with order 1. So x0 is equal to plus or minus 1, and that implies that we have roots at x equals 1 plus epsilon plus dot dot dot. But we also have roots at x is equal to epsilon to the minus 1/2 and x is equal to minus epsilon to the minus 1/2. So notice that as epsilon goes down to 0, last two roots go to plus or minus infinity. And the way to think about this is just to sketch out our cubic here and to notice that it has a form that looks a little bit like that. And as epsilon increases, this thing here stretches out. So this is our, this goes like minus epsilon to the minus 1/2, and this one here goes like epsilon to the minus 1/2. And that's what's going on with these two roots. Now, if you want to see a little bit more of this, some recommended further reading. John Hinch's Perturbation Methods book is excellent, and sort of in the same vein as this is the Part 2 Asymptotic Methods course, and you can find some notes online for that here as well. Any questions or anything that's not clear, email me.